आपसे भी पूछूंगा ताकि मुझे कुछ इदराक हो जाए मामलात का, ठीक है? Should we begin? Okay. So, morning everybody. So, I'll start with what I intend to cover. Of course, by no means thoroughly. So, we will skim through certain things, but so I'll begin with the introduction to so it's been ages that I have not used the chalk, so that's a learning curve for me. Introduction to differential equations, and of course, ordinary differential equations here. So this is ordinary differential equations. I'll come to this in a moment. And in this, I'll talk about linear and non-linear first order, let me write differential equations, and I will then talk about linear second order differential equations, and I will also talk about after this, so there will be a category of homogeneous and inhomogeneous ODEs, and after that I'm going to talk about Green's function in the context of ODEs. So I will have to go till variation of parameters, and from there I will develop this concept. So mainly I'll be following Dennis Zill and Riley and Hobson's. Shamama will give you the PDF of those two books, okay? There are many editions, so that doesn't matter actually. Okay, and then we will talk about, that's a lot of stuff actually, because you see, variable coefficient ODEs, and these are, I'm talking about homogeneous ODEs, right? And then of course in this context we will talk about power series. Then depending on the variable coefficient differential equations, we will have singular points, and in this context removable and irremovable singularities, and then we will talk about the Frobenius series. So I have a question to ask from Essen. So Essen, have you introduced them to the concept of orthogonality of the functions? So inner product. Okay, so if you have been introduced, then probably I'll skip, because then I'll go on and talk about Sturm-Liouville problem. And that is where I'll end. Okay. So if I say that I am dealing with ordinary differential equations, so in terms of calculus, what comes to your mind?
Single independent variable.
Okay. Okay, so let me give you an example and then pose the question again. So let's say if I say x square plus y square is equal to r square, what kind of an equation is it? Okay, so immediately when I write down an algebraic expression, there is a geometric shape that comes to your mind. So algebra and geometry, in maths, everywhere, when you want to write something, there is a corresponding geometric shape that also comes to your mind. So when you say that you are dealing with ODEs, then essentially in terms of calculus, what I'm talking about in terms of geometry. So we are dealing with lines, okay? And if I talk about multivariable calculus, then I mean to say I'm going to calculate the areas and volumes. So, and that will eventually get translated into PDEs when you have, so multivariable calculus, the next thing is the PDEs. So that is a function dependent on more than one variable, right? So that is one thing. So in this whole course, we are going to talk about, and we are going to confine ourselves to the single variable calculus. The only exception here, जिन्होंने BS कर लिया है and they have done ODEs, tell me where is one exception where I'll be dealing with ODEs, but essentially I'll be encountering the multivariable calculus or PDEs, so to say. वेव इक्वेशन जो है वो क्या है? वो पीडी है, तो हम तो ओडी की बात कर रहे हैं. क्यों जी? लायबल. ODs पढ़ते पढ़ते we will come across something where actually we will be dealing with the partial differential equation. That will be the only instance where we'll be exact equations. Yeah, okay. So we will have some kind of idea over there. What is the basic difference when you solve a PDE and when you solve an ODE? So why do we bother to do that? First thing is that when we model the physical systems, we come across these equations. For instance, can you tell me where do you encounter the first order ODEs? आपका नाम क्या? What is your name? हाँ, तो अहमद, आप A levels के हैं, तो I would, you are less exposed than others. So if you answer, I'll assume the others also have some kind of an idea. So were you exposed to the idea of differential equations in A levels?
Yes.
Okay. You took up mathematics in A levels? All right. Okay.
So, sir, what's your question?
My question was that what kind of physical models, you can recall where you have an ordinary differential equation, let's say first order differential equation.
You could say like acceleration, velocity, those are easily.
But acceleration is not a first order thing.
It's second order.
Yep. So let's. Oh, well, Hooke's law again. जब आप force की बात करते हैं ना, तो you talk about the second derivative, right? Hooke's law again, F जहाँ पे आता है ना, तो F is ma. So this is one other thing that I want to say, that mostly we will be dealing with F is equal to ma, and why we do that? Because this is the way nature behaves. Nature does not behave as F is equal to mx. It does not behave as F is equal to mx dot. It behaves as f mx double dot. And all these things that you see over here, they tell you that it is non-trivial that nature behaves that way. So it tells you about a very deep mathematical structure, and it happens because nature behaves this way. So eventually we would like to write everything down in terms of a stumble-wheel problem so that we can make some comments about it. And there are a lot of stuff that we do in these variable coefficient differential equations that is actually motivated by that. So for instance, आप orthogonality पढ़ते हैं, different आपने पढ़ा होगा, orthogonality of Legendre, orthogonality of Bessel's, orthogonality of Hermite polynomials, So why does orthogonality? So the answer will eventually be given by this thing. that you can actually recast every second order differential equation in Sturm-Liouville form. If it is not in that form, you can recast it so that the properties that the Sturm-Liouville problem has, the same problem will also have the same properties. Okay, coming back the question. So radioactive decay is one example. dN over dt is equal to minus lambda n. Yeah, let's say we can say it is proportional to n. Something like that. Newton's law of cooling. If you write down Kirchhoff's law in current form, you will have a first order differential equation. So now I am going to begin from the very basics. So generally अगर आप differential equation की बात करते हैं तो what does a differential equation mean in your view?
Relative change of variables.
Change of variables,
Rate of
Rate of
rate of change, but how things change in the world around you. That is the question that you need to ask yourself. What is your observation? For instance, F is equal to ma, what does it tell you? So things either change in space or they change in time, right? So because we are going to deal with single variable calculus, so we can either say we have a dy by dx, or I will say that I will have a dy by dt. So how many of you basically understand this thing, that what is the fundamental difference between this and this? In terms of your understanding of how things change with respect to something. Does it represent an evolution? Good. So time के साथ जब कोई चीज़ when changes, so that deals with the evolution. So you can have something which is, let's say, dy by dx is equal to f of xy. But you can also have something which is changing with time also. It could be anything. It could be like this also. Newton not only told us how nature behaves macroscopically, but he also developed simultaneously the mathematics to explain it. Okay? So that is why we know now that there is x dot and there is x double dot, and there is a physical meaning associated with all of this. This is space, this is velocity, and this is acceleration. So what if you go on to the higher order derivatives? Can you associate any physical quantity with them? Oh, but that is dA over dt, right? The main thing is, it's not a new physical quantity. It is just rate of change of acceleration. You call it a jerk, right? आप लोगों में से कोई किसी ने statistical physics पढ़ी है, moments लिए हैं कभी आपने distribution function के, तो वो भी अगर आप लें ना तो आप 0th moment लेंगे तो number density आ जाएगी, first moment लेंगे you will have velocity, second moment लेंगे you will have energy equation, but if you take another one, you can't associate a physical meaning to it. So because you are limited by this thing, right? So, लेकिन अगर आप in terms of तो coming back to the same question कि जब आप एक differential equation देखते हैं तो what else comes to your mind, because this is something which is developed on the idea of calculus. So what kind of an equation is it? Geometrically speaking, slope, yeah. So slope के साथ ही what is the thing that comes to your mind? Tangent to a curve, right? तो ये tangent भी आपको ज़हन में आता है. तो जो ही ये चीज आपके पास आती है, and if you have the concept of calculus, what else comes to your mind? What are the things that these things ought to have? Continuity and differentiability. Okay. टेलर सीरीज आपने पढ़ी है? टेलर सीरीज में अगर आपके पास कॉर्नर आ जाए, it fails. Because it's an idea associated with the derivatives. So anything which is associated with the derivatives ought to be differentiable and continuous. And because you are dealing with an equation that involves derivatives here, so the same idea of continuity and differentiability holds here. Otherwise, it won't make any sense. All right. What else? Okay. So I think with this, I'll just, so let's say I write this equation. So this is something which involves derivatives. The idea of continuity and differentiability, is applicable here. And let me write something else now. So now that we are talking about nomenclature, so okay, if I want to solve it, what do I need to do? And it's not separation of variables, don't get into that. So the idea is, if you have a derivative and you want to get rid of it, you need to take the antiderivative, right? So the antiderivative of this equation will give you a solution, right? So the whole idea of solving a differential equation is to take the antiderivative, and that will give you a solution. So why you are interested? So this is the dependent variable, this is the independent variable. So if you are going to plot something, it will be y versus x. So all that you are seeking in this particular case is how to find y. That is the entire pursuit of this whole particular series of lectures, that you are supposed to find y. And that y can mean anything in terms of physics. It can be, this n, it can be, let's say, I write down this is a charged particle subjected to a magnetic field, and I want to. तो एक चीज और मैं आपसे पूछना चाहता हूँ before I go on. When you do f is equal to ma, आपने नहीं बोलना बीच में. What is essentially that you are trying to find? Once you solve this equation, what is the information that you get eventually? So let's say, अब आपको पता है when a charged particle is subjected to a magnetic field, what happens? No, there is a force on it, we know. But what happens when a charge, experimentally, if you subject,
Sir, when you throw it perpendicular, then it performs circular motion.
circular motion, okay? So without solving this equation, you can come up with the answer, and what is that? Sine. All that I'm trying to say is, essentially what you get is this thing. So this thing gives you trajectory of the particle. Okay? That is your fundamental goal once you are through with everything. So without solving it, it involves some understanding of differential equations. You will have to write down this equation in components form, then you have to do some algebra, and eventually you will end up with this. But the idea is that if you are doing this, अभी हम क्योंकि first order पे जाना तो अभी मैं सवाल नहीं करता, लेकिन now you know कि what we are actually want to do. We want to find an unknown, and for a physical system, that unknown means something. That is like finding something like a charged particle subjected to a magnetic field, and you get a circle, and you have found out something very important. Similarly, Newton's first law, in principle, if you understand the differential equations, then in the absence of a force, a particle will traverse a straight line you should be able to mathematically work it out. So you don't have to perform an experiment as a theoretician. Although it's an empirical law, but if this empirical law is given to me, then I can say in the absence of a force, the Newton's first law statement, I can bear it out. This much you understand? I mean, we will do it, but because we are not dealing with that, so anyway. So this is one thing that I wanted to tell you. The other thing was, what if I write this thing? What do you understand by this? Harmonic oscillation. Harmonic oscillation. This is a non-linear ODE. So I told you that I'll teach you linear and non-linear ODEs. So just remember, anything, any power other than 1 of the dependent variable gives you a non-linear ODE or a PDE or whatever. So just tell me, what about this one? Oh, well, okay. What do you think of this? How many of you think it's linear? All right. You, Ahmed?
Sir, it would. I don't think it's linear.
You don't think it's linear? We have just defined it. It depends on the power of the dependent variable, not on the power of the independent variable.
Yes, sir, but like solving it in my head, it would be something like y is equal to e power x, something like that.
No, that's another thing, but the thing is, how do you qualify a linear from a nonlinear differential equation? So it depends on the power of the dependent variable. Okay? I'm not saying that this term is linear, but this differential equation is linear because the dependent variable has power 1.
Okay.
Got? It's all about nomenclature, right? So what if I write this? Good. So now you understand this. Anything other than 1 is nonlinear of the dependent variable, right? Good. And what about this one? Q, Ahmed?
Non-linear.
How do you know this?
I would say it's because the dependent variable is inside a cos function, like something like that, because cos is also non-linear most of the time. So it would.
No, but what makes you say that? मतलब मुझे ये देख के जब मैंने ये देखा, okay, so अब आप इस तरह से इसको आपने non-linear कह दिया.
Yes, sir.
Just looking at the graph, okay, that is one thing. It's not a linear thing. Yeah, but if you have to convince yourself in terms of the definition that we have just developed, then how would I establish that?
Okay, that's
Yeah. That is why it is. अभी हार्मोनिक ऑसिलेटर कौन कह रहे थे? आप कह रहे थे. तो हार्मोनिक ऑसिलेटर कभी भी नहीं हो सकता ये, बिकॉज ये फर्स्ट ऑर्डर है. ओके, सो सेकेंड ऑर्डर डिफरेंशियल इक्वेशन वो बनती है बिकॉज now this is okay, right? Okay, right. So this much we have done. Partial differential equation, on the other hand, of course, you know, is this. अगर ये इक्वेशन मैं लिखूं and if I find the value of u, no matter which method I adopt, what do you think u will be a function of? X and y both, yeah. So, by its very definition, it is a function of two variables and, all right, chaliye. वैसे, if you look at this, in terms of geometry, can you say something about it? EMT पढ़ ली हुई है आप लोगों ने? This is Laplace's equation, but if you just try and observe this equation geometrically, what do you think? Sine और cosine बनेगा आपका ख्याल है? No, but just when I write down a second derivative, anything comes to your mind? Exponential? How? ये क्यों कहते हैं आप, मतलब exponential? How come a second derivative is related to an exponential? Second order derivative जो है, what does it tell you? Which thing it is associated with in geometry? Extremum points, yes. So if the first order derivative is 0, then it tells you it's an extremum point. But whether it's a maxima or a minima, you can't tell. So you have to take the second derivative and then it will tell you whether it's a maxima or a minima. So when I write down this kind of an equation and it gives me 0, what is it that you can infer from it, geometrically speaking? जब एक का मैक्सिमम होगा तो दूसरे का मिनिमम होगा तो it will give you 0. If two quantities are written in terms of positive and they give you 0, so they ought to have opposite signs to give you 0, right? So just to remind you कि वो आप जब पढ़ते हैं कि it doesn't admit a local maxima or minima, तो ये एक ऐसी बाउंड्री सी बन रही है. ये इसकी क्लासिफिकेशन और चीज़ है, मतलब ये elliptic है, hyperbolic है, parabolic है. So we are not going to indulge in that. This is beyond the scope of these lectures because I am going to focus on the single variable calculus. Okay. ये nomenclature वाले मामला तो हल हो गए. इस equation को आप इस तरह भी, जो nth order differential equation है, उसकी most general form is this. If it is homogeneous, this is the nth order homogeneous differential equation, linear differential equation. And if you have this, then it becomes non-homogeneous or inhomogeneous ODE. Okay? All right. इसको हम इस तरह भी लिखते हैं. X, Y, Y dash up till yn is equal to. So this is the way to describe it. Generally, when you take the derivative with respect to space, you do the dashes. And when you have, so x double dot I wrote down because this is d2x over dt square. So this is a dot, but it is also derogatively called the fly speck notation. So you have dots over there when something is changing with respect to time. So when you are dealing with a particular course, you first of all, the jargon is also important to understand, right? That how do you express things and what they essentially mean. This kind of a differential equation, let's say I can write down a first order differential equation as f of x, y, the same equation in first order, and a second order differential equation can be written as in this particular form, this is called the normal form of the differential equation. So this is the normal form. Just to acquaint ourselves with how things are written and what are the names given. All right. Okay. Another lesson that you need to learn is that differential equation is defined over an interval, right? So let's say in Legendre's differential equation, you write down -1 to 1, that deals with the singular points and stuff like that. Similarly, in Bessel's, you have a different way of writing it. So they all deal with, but differential equation itself, isn't defined over an interval. And once I take the antiderivative and I find the solution, how do I know that it's a solution of the differential equation? What do I need to do? I have not talked about the boundary conditions at all. Whatever the solution, you need to plug it back into the differential equation, and if it gives you left hand side is equal to right hand side, then it is verified. So there is no other way. So I have seen many technical papers where they assert that this is a particular solution to this differential equation. The moment you plug it in, it doesn't give you 0 or left hand side is equal to right hand side, so it's a false claim. So verification is the first thing that you do to know that you have embarked on the right path. So this is something that you should always check. So that is something that you must do. The verification of a solution की भी बात उसने की है. Now there is a very important distinction that you need to make. Function versus solution. Okay? So let's say if this is the solution of a differential equation. Okay? And I write down, in fact, draw the graph of it. So what do you think the graph would be? No, not interval, just graph. Just draw the graph.
Sir, at 0 it will be vertically up to infinity.
Mm-hmm.
Then it will be decay.
So is it the right way to describe it?
Yes.
Mm-hmm. So it blows up at x is equal to 0, right? So now tell me, this function, can it be the solution of a differential equation?
It depends on the domain, like because there's a singular point where at x is equal to 0, we can't have it as a solution to a differential equation because there would be a point where there would be no value. It isn't continuous.
Yeah, so the whole idea is that if this is the solution of a differential equation, that it would either correspond to this interval or it would correspond to this interval. This whole thing can never be the solution of a differential equation because it has to be defined over that. It has to be continuous and differentiable, right? So that is something that you need to know. So these are the things that I think I would like to share with you because these are the points that are generally not discussed. So this is very important, function versus solution. So you need to know what it is. So I'll go on to talk about something else also, but the solution bhi ho gaya, function versus, the other thing is, explicit and implicit solutions. So let's say I write down, what do you think this is?
Explicit.
What about this? Ahmed, बताओ.
No, this is implicit.
And why? What makes you say this?
Because you can't have y wholly in terms of x. Without you having to take a square root, then you would have like two domains.
So when I say explicit, it means something ought to be written like this. In this particular case, that is not the case, and I just need to write this thing down as, and now it is in that form. So this is the explicit expression.
Is that question?
Yep.
But like in this equation, there's like plus minus the sign x. Would that change anything? Because
It does when you talk in terms of a function, and you know that circle is not a function but a semicircle is, because it fails the vertical line test. So you can't afford to forget the calculus, right? Newton developed the idea of calculus to explain the physical world. So these are the tools with which you understand the world around you. And all these have a meaning, an associated geometric meaning. So in order to visualize, you need to understand this thing. Anyway, so this is what explicit and implicit mean. Okay.
so one more question.
Yeah, please go
Here
on.
you actually were able to write y in terms of x whole. But it was like you had to take a square root now. But in like a specific problem, you might only care about the positive side.
Yeah, so I mean, I don't have to write this. If I write x plus y is equal to c,
Yes.
it is still in implicit form, and I have to write y is equal to c minus
So
x.
that would be, you turned it into an explicit form.
Yep.
Okay.
Yeah, so that is what implicit and explicit mean.
Okay.
That when I can express y in terms of x, that is explicit thing.
Okay.
So if the
I thought it would be like if you're unable to express y in terms of x.
No, then what are we trying to do if we can't express? Because that is the whole idea. Because let's say if you are solving a differential equation, the whole idea is to express the dependent variable in terms of the independent variable and then draw it.
Yes.
Chicken. Not necessarily every time you get something is going to be in the form of a function. Transcendental equations bhi hoti hain, but I'm not going to
Okay.
go there. But yeah, here we have functions that we can plot.
Sir, is there an example of an implicit solution that you can't write in explicit form?
Can't write.
Or is it always that if you have an implicit solution that you can find its explicit?
Yeah, so there can be all kinds of very tricky expressions. You see, let's say,
Even within physical systems?
I mean, mathematically speaking, you can now, whether it corresponds to a physical system, I just can't think of any. Do you?
I mean, look at very simple example. Look at 1 plus x square plus x5 equal to. तो इसके कितनी solutions हैं?
5.
Theory है ना, but
Yeah.
you are ensured that there are solutions, but you can't solve it explicitly. It's something like that. The theory will tell you that there are solutions, but you can't always.
But that's an equation where we might not be able to find a solution,
But theoretically, you know.
theoretically. But if you have something that involves x and y, they can be tricky forms. But yeah, I mean, in general you should be. But sometimes you may not be able to separate. I'm just trying to make it. How can I make that? Maybe 2/3, 4/3 here, and maybe 5/3 here, you know, and that is equal to r square. So already you can see that it
But
would
here-
be kind of tricky, but still you can do it. It is still doable. It
In
is
this
still
case,
doable.
it is doable.
It is still doable. I won't say it is not doable.
Different question. He told us about the polynomial x power 5 wala. You can't really solve that, लेकिन you can get numerical solutions.
Yeah,
with
yeah, of
combination
course,
methods, ना? Is it ever possible कि you aren't able to do that? मतलब equation इतनी मुश्किल है कि numerical methods don't work or it's difficult.
Could be a possibility
Is
because
there an example of that?
I can't give you an example of that. But of course, the tractable equations हैं आपके पास वो they are finite. You can have many difficult equations. So, for instance, Einstein's general relativity equations, these are nonlinear coupled PDEs. So, with many assumptions you can find, for instance, Navier-Stokes equations. So, unless you make assumptions, it is still a problem that needs to be solved in its full glory, right? So, you can have those equations. Again, because mathematics is being taught to physicists, so you must understand that it's a game of approximations. Let me give you an example. So what if you are trying to solve this equation? It can be an extreme mess for you, right? If you take the whole series. But if you have let's say I write down like this. But if you have a small angle, motion, so sine y will be y and you will come up with an oscillatory solution. So this is the essence. Physics is a game of approximations. The great Paul Dirac said that, in mathematics and the mathematicians, they try and solve intractable equations. A physicist comes along, he does an order of magnitude analysis, retains the terms that ought to be retained and throw away the other terms. And most of the time he comes up with a very acceptable and agreeable solution of nature. So physics is a game of approximation. So when you don the hat of a physicist, you ought to be smart to understand which particular terms are going to make sense in this particular system and what are the terms that you can afford to throw away. And you can get a very good answer to the reality. Okay. dy by dt is equal to y, let's say when you solve, whatever method you do, so y is equal to something plus a constant, and this c is the arbitrary constant. So it can assume infinite values, but this is one constant. But if you are solving, let's say, second order differential equation, you will have two constants. And if you are solving an nth order differential equation, you will have n constants. This is like a family of solutions that you can get. N parameter. So first differential is associated with one parameter, 2 with 2, 3 with 3, 4 with 4, n with n.
Right.
So we call them family of solutions. But this is, for first order it is one parameter, for second order it is two parameter, for nth order it is n parameter. The families of solutions are just okay. And if you change C, it will change the whole thing. So why do we bother to find this C, and why to place this C here?
Because we are solving the equation generally for a phenomena, and we can have many trajectories for that phenomena. So when we actually put the initial or boundary conditions, we are actually picking one trajectory for that. For if a particle is moving in wind, for
Okay, so
example.
let me give an example here. So let's say the solution is this line.
Yeah.
So if this is the solution, I can plot infinite of them,
Yeah.
right?
Right.
But which particular curve I need to pick,
It depends on the boundary or initial
that will be
condition.
determined by C. That is why we are interested. Okay.
Right.
So I'm going to talk about the initial value problem, but so initial value problem is a way to find C. See, arbitrariness is then removed and you get a particular solution. So let's say I can solve a differential equation which have, you see, these infinite concentric circles. But which particular circle I will ride on, I will be directed by the initial condition. So initial condition is a directive. It tells you which one to pick for your system. That is why it is called a particular solution, because then C assumes a value. So I'm going to dwell on this, but before that, there is something else that I want to talk about, and then I'll go and it's interesting that I would like to talk about before I go further. तो इनिशियल वैल्यू प्रॉब्लम की बात अभी हमने की, चलें थोड़ी सी इसके बारे में और बात करते हैं. Let's talk about it. So let's say there is a differential equation. So y dash is equal to y is a differential equation. The solution is y is equal to c e raised to power x. So I am not bothering myself with how I find it. We have not discussed any method. It's just that we have been given this solution. And I have been given two conditions. Y of 0 is equal to 3 and y of 1 is equal to minus 2. So you guys should calculate for this, and you guys should calculate for this, and tell me what is the value of C that you get, and now tell me what essentially happens here.
3. So y equals to 3 into e raised to power x.
minus 2 divided by
तो ये इस केस के लिए
Yes, sir. Y
C3 आ गया आपके पास, तो y is equal to 3 e raised to power x आ गया, and in the other case you will have
minus
Minus 2 by e.
तो इससे ऊपर जाएगा minus 2 e power x
minus 2 over e.
then I assume that you have calculated it
X
correctly.
minus 1.
Now,
X minus 1.
x minus 1 होगा.
X के साथ minus 1 होगा.
e power x minus 1
ये कह रहे हैं
No.
x minus 1.
So x
Sir, actually it's minus 2 by e. So e
Minus
का
2 by e है.
I'll just see what it is. और 2 by e है, okay. अब ठीक है,
yeah.
तो minus 2 by 2 e raised to power x minus 1. Okay. But the thing is, what is the point here?
For different
X 0,
initial
y 3. And what about this one?
1 and minus 2
X 1,
Why not?
y minus 2. So let's say this is 1, this is the point. So the directive is you have to go through this point. So whatever the solution you have, immediately you realize that whatever solution I have, I will have to choose this one. Although there will be this solution as well. There will be a lot of. One thing that it has done is that out of all these curves, it has selected one curve because of the directive. The other thing is, because of different initial conditions, you move in different directions.
Yes.
Just because the directive says your curve ought to pass through this point. So not only that you get a particular solution, you also decide in which quadrant you will move. So it's a very non-trivial thing. This directive has very non-trivial consequences. The solution doesn't change, but which part of the solution you end up with is decided by that.
अगर हमारे पास एक से ज़्यादा वेरिएबल्स हों, then what happens?
Then things become very messy. I'm going to talk about the autonomous differential equation and the phase diagram, so I'm going to tell you why it's so easy. And when you have just one more variable, you will be in a huge fix. Because one thing is changing with respect to two things. Let's say, अभी मैं करूँगा लेकिन अभी just to tell you, dy by dt is equal to y and dy by dt is equal to x minus y. So these are two very different things, because over here the dependence is only on this variable. The slope changes with respect to just this, but over here the slope changes with respect to both of them. So the slope is not constant, and it is such a great facility to have a slope defined by one thing rather than by two things. क्योंकि देखिए ना, अभी चलो मैं I'll get back to this because I am going to talk about it. So let's postpone this discussion for the later point. So now I would like to talk about something else which I always find very interesting. Discussing all this is important because it's not about just giving you a method and solving something. You need to understand the consequences because you are going to, make conclusions about how the physical world behaves, and they are governed by these equations. So they are all intimately connected. So there is a differential equation y double dash plus 2x y square is equal to 0, and subject to initial condition y of 0 is equal to minus 1. The solution that you get is 1 over x square plus c. When you plug this in, it will have 1 over x square minus 1. So this is a particular solution. Now let's plot it. So as you can see, at x is equal to plus minus 1, this function will blow up, okay? So there's a 1 here. So my solution now behaves like this. Now I'm going to ask you 3 questions. So consider as a function, this is how this function would behave. Okay? Consider as the solution of a differential equation, what are the intervals where you can talk about the solution? There are 3 intervals that I can see. Tell me what are those 3 intervals.
Minus infinity minus infinity to minus 1
Yeah.
Minus 1 to 1
and
or 1
1
to plus infinity.
क्या लिखे हैं यहाँ पे?
X is less than minus 1.
Sir, open.
It should be less than minus 1 and greater than, oh well, it should be greater than minus 1 and less than minus infinity. It should be greater than and less than, greater than minus 1 and less than 1, and then of course again greater than 1 up to less than infinity, right? So these are the 3 intervals that you have. What about if you take into account this directive, then what about the solution?
It will be in pairs of C.
C तो मैंने find कर लिया, I found it. That is why I wrote, if I put this is the solution. I have plotted the solution as a function. This is the whole range. As a solution of a differential equation, we have found out that only in the intervals where it is defined, I can talk about the solution. But now, strictly speaking, in terms of this directive, what is it that I am allowed?
-1 to 1.
So -1 to 1.
Middle one.
Huh?
The
But why do you say that? Okay, answer is correct, but
initial value
why?
problem is
Bata.
So because you found -1 to get
-1 kya? What is the point?
The domain here is 0, which is in.
0 -1 कहाँ होगा?
उसके साथ
Because of the directive. So for this particular directive, you must pick this. Although in principle, this can be a legitimate solution of the differential equation. This is the legitimate solution of the differential equation. This is also the legitimate solution of the differential equation. But because of this directive, only this one you are bound to pick. So I think I have tried to explain to you that solution and function. Sorry, please.
So what would we then say? Would we say that there are 3 domains for this one solution? Or would
Yeah,
we say
these
that
are the domains. Yeah, so thank you very much. So these are the interval of existence, domain of the solution, whatever you want to call. These are all the names. Interval of existence bhi keh sakte hain. But this directive forces you to pick only this region because you direct it to pass through a certain point. And of all the different domains, this is the only curve that passes through that point. So
So अगर इस तरह की shape की हमारी vector fields हो, ठीक है, and let's say it's like a water flow problem. During the asymptotes, what would happen to, like, let's say a leaf moving in water? Would it go this way, or like, so एक तरफ जाएगा सिर्फ हमेशा, or is it possible that it changes direction?
it depends on the differential equation that you are dealing with. I don't think that will be explained by an ODE.
I mean, like, let's say in this shape, इस shape की form के अंदर एक vector field है, उस vector field के अंदर जो asymptotes वाला जो हिस्सा आता है, what would happen to the flow over there?
What relevance does it have with this particular discussion? I don't understand.
So I was wondering कि मतलब कि जब asymptote के करीब बात आती है,
Asymptotes तो यहाँ भी हैं. You see the asymptotes here?
Yes.
This is an asymptote. This is an asymptote. This is an asymptote. This is an asymptote.
physically वहाँ पे क्या हो रहा होगा? I mean,
Physically, you can never reach that because it blows up over there, and that is the meaning of asymptote. If you draw tangent x, so you will have this thing, and these are asymptotes for tangent x. The asymptotes you never reach there because the function blows up at that point. Okay. Now there is another very legitimate question for a physicist and of course a mathematician, whether the solution of a differential equation exists, and if it exists, whether it is unique. Okay. So I was talking to a mathematician, Hassan Saab. So I said, you have heard about this Pickard Lindelof, theorem. So he said, generally we were never taught this and all. And I said, what is the essence of the Lipschitz condition and this and that? So that is why I thought I should. So we are not going into the nitty-gritty of how it is derived and all that. The theorem is proved, but the point is that this is the very legitimate question in mathematics, and when you're solving a differential equation, that whether you will be able to find a solution, whether a solution exists, and the other question is whether it will be unique. So for instance, if you're finding the analysis of stability of this structure, so if you come up with 19 values, that's ridiculous, right? A force is being applied and you come up with 5 different values of acceleration. Nonsensical, non-physical. For a particular force, you will have a particular acceleration, right? So this is uniqueness is very important for a physicist, because there ought to be a uniqueness, and of course the existence of a particular solution. Abhi, you were asking this, whether a solution exists or not. So the basic thing is existence and uniqueness. So the same idea goes for the second order differential equations, but I'm just going to give you an idea of what this existence and uniqueness theorems. Existence and uniqueness theorem. The tool with the help of which you answer this is Lindelof. अब वो क्या कहता है? Let's try and understand. First of all, I'll give you an example. First things first, we have talked about the initial value problem. When we are going to discuss this, we are going to discuss it for a first order differential equation written in, let's say, this normal form and subject to a condition that y of x naught is equal to y naught. So this is applicable to an initial value problem. Okay. First, let's try and see what happens. What is the problem here? This is the first lecture, that is why we need to, kind of look at these things. These are the nitty-gritties of differential equations. Then we will come to the methods and the application, but all these considerations are extremely important. So let me write down 3 equations and let's see what is the lesson that we learn from there. Subject to y of 0 is equal to 1, y dash is equal to y minus 1 over x, y of 0 is equal to 1, and y dash is equal to 1 over x, y of 0 is equal to 1. All right. So if I solve this equation and substitute this value, I will have y is equal to x square over 2 plus 1. If I solve this, I will have y minus 1 is equal to cx. And if I solve this, I will have y is equal to log of x plus c. Okay. पहले इनके बारे में बात कर लें हम, then we will move forward. Okay. So if I plug this directive, I get c is equal to 1. This is a unique solution, right? Because I have c is equal to 1 here, corresponding to the arbitrariness has been removed by that directive. Now look at this. Plug it in here. Now tell me, Nishad, this time I will ask you. Tell me, y minus 1 is equal to cx. Now you apply the initial condition and tell me what happens.
We can't find c because if we put x equals to 0,
Yeah.
it would 0.
No, in terms of equation, if you just substitute it, so 1 minus 1 is 0 and x is 0, right? So,
Undetermined.
what can we do? C can take on any value. Wonderful. So when it can take any value, what does that mean?
C is all
Infinitely
real.
many solutions. So from here, there is a differential equation for which you have a unique solution. Here you have infinitely many solutions. Now what about this one?
Undefined.
No solution.
No solution, why?
Log
Because
of
ln x
four.
is undefined.
Aap batao.
ln x is
Yeah.
undefined. So there
Why
is
the
some-
solution doesn't exist?
Because ln x is undefined when it's x is equals to 0.
Yeah. Log is not defined at x is equal to 0. So no solution. So this is to convince you that this is where the problem comes from. That you have an initial value problem. Depending on the initial value and depending on the differential equation, you can come up with these three different situations. So that is why you associate yourself with this question, whether a solution exists, and if it exists, whether it is unique or not. Okay? All right. So that is one thing. The next thing is the criteria. So I'm going to just write down the criteria. Okay. Write down the criteria for that. So for that, I need to draw a rectangle. So I am talking about the point x naught. In the vicinity of this point, I am going to draw a rectangle. So corresponding to this x naught, I will have a y naught. And this one is, let's say, so this whole thing is y naught minus some point, so you can say y naught minus b, and you can call this y naught plus b, and you can call this x naught minus a, and you can call this x naught plus a. How do you call it? Because the box is defined that way. I write x minus x naught is less than a, and y minus y naught less than a. Calculus, when I write something like this, so what does that mean? What is it that I am specifying on the real line?
Domain and range.
No, just this modulus less than something. What does it mean? Inequality.
Sir, interval.
एक
Dimension of this one.
Symmetric about 0. Let's say this is the line, and I write this is the horizontal line, and I say x minus x naught modulus is less than a. So essentially what it means. Yeah, because you can write this as okay, distance ki baat hai. So you are now defining the boundary of your box, and we are not including the endpoints in this particular theorem, so it is called an open rectangle. So statement goes like this, that if in this region x minus x naught modulus less than a and y minus, first things first, you need to understand that we talk about an interval, and when you talk about an interval, basically you talk about the local region, the neighborhood. अगर आप टेलर एक्सपेंशन भी देखें तो you kind of find something in the vicinity, in the neighborhood. So यहाँ पे भी you are kind of trying to assess something in the neighborhood. So the criteria deals with that. Essentially, it again deals with the continuity and differentiability. Okay? So it says that if this is so, and A and B are greater than 0, and A, B belong to real positive, then if f of x, y is continuous within that defined region, then you will say that the solution exists, and if curly of f over curly y is also continuous, then you say that unique solution would exist. So I'm going to give you an example, but this is what the Picard-Lindelof theorem basically is, and this curly f over curly y is the Lipschitz condition. So if you want, you can dig deeper and find out the examples of Lipschitz condition and how they are incorporated in the Picard-Lindelof theorem. At this point, I didn't think that I need to kind of tell you about the proof and stuff like that, because that also would mean that I also need to go through some stuff. Parvesa, when you were taught calculus, were you taught Picard-Lindelof theorem and the proof of it? I don't think so. It is being used as a tool to, give you an idea of the existence and uniqueness of.
All you need to know is what it is.
Yeah. So I'm going to tell you what it is, and that would be good enough. Yeah. So that way we are going to. Okay. All right. Any questions? So this is just the theorem. We need to apply this theorem, and we will be done with the existence and uniqueness. But this is very important to know, of course. Very soon you will find that it is, a sufficient condition, but it's a necessary condition, but not a sufficient condition. Because let's say I write down dy by dt is equal to 1 over t, so I know that t is equal to 0, but there is a singularity. But I can always choose some region away from this where I do not have to deal with this. So the solution would exist, right? So it also depends how you define your interval.
Sir, but physical system में हम कैसे define करेंगे?
Physical. आप जब कहते हैं Legendre में -1 to 1, so all that you are saying is that within the confines you are dealing with something, you are not really dealing with anything else. When you write down a solution, y is equal to 1 over x, I just wrote. When you do that, this is what you get. Does that mean that it doesn't exist? It exists fantastically well for a very large domain. Only at x is equal to 0 that you will have an asymptote. So let's say if you pick something here, something here, something here, something here, will you run into any problem? No. It is continuous and differentiable. You don't have to bother about anything.
All right.
Clear? Good question. Yeah. That is something that. Okay, so let's talk about a particular problem. So let's say I have y dash is equal to under root y plus 1, and I have y0 is equal to 1. So now tell me, from this IVP, can you write down this thing? Go ahead, tell me.
Sir, x तो है ही.
X naught is 0. Y naught is 1. So from there you can actually define your rectangle. So in that, if you look at this function, if you put y is equal to 1, the function is continuous, right? So it is guaranteed that the solution exists. But now you take the, yeah, because This is the function that we are talking about. So f of xy, whatever it is under root y plus 1, and we have just put 1 and it is okay. But now take curly f over curly y and see what happens here. This becomes 1 over
Under root y.
Y is equal to 0 and y.
but this is not y is equal to 0.
Y equals to 1.
So this is all that you need to, involve yourself with. But as y goes to infinity, or y goes to 0, sorry, this becomes infinity. So over there you just don't know what happens. So when y goes to 0 and this becomes infinity, then you don't know what will happen and you cannot say anything about the uniqueness. But for this particular interval you can say something. Over there you do not encounter that problem. Okay? So these are the things that you need to be concerned about. You define your interval, you take the derivatives, and this kind of problem always happens when you have a nonlinear equation. This is again a nonlinear equation. Because when you take the derivative, this goes down and then the problem of blowing up of a solution comes. For a linear function, you will never encounter this. So remember that all these things basically are designed for the nonlinear functions. Because they always give you this kind of possibility of something going in the denominator and blowing up a function. As long as they're in the numerator, nothing happens.
Are you going to determine this interval a and b from this condition?
Yeah, so x is, let's say, it's this, and my y minus 1 is less than b, but you will have to define these constants also. For a realistic problem, then you have to give some value. But in principle, all that I need to say is that now I will have b plus 1 and minus b plus 1.
No, what I mean is that from this condition, this differentiability of f, I think you can determine that b. So it's if y goes to if f partial f by partial f partial y goes to infinity at y is equal to 0, then that means that you can go down from 1 from y naught down to 0, and yeah. So that's the interval.
But the thing is,
so
my point is
like
0 and 1,
yeah,
right?
yeah, those are central points. Yeah,
Yeah, so
but the interval.
yeah, so around those points, if in the vicinity of those points I also encounter something where 0 is also there, then of course I cannot guarantee uniqueness. The whole idea is all those points where this function is not continuous, you cannot guarantee the uniqueness.
Yeah.
So for that you have to take into account the Picard's recipe of doing things and find out what you can say. So I'm not going to get into that, but
no, I guess you can determine that b from this condition, and you can exactly pinpoint the whole interval. So I mean, otherwise if a and b are undetermined, then you don't know how small or large that interval is. So
true. Yeah, that's very right. What is the problem given here to us? So, but again the point is this a and this b ought to be given to me. I can't find a and b. How can you find a and b here?
yeah, so for this condition, you know that it's not satisfied at y is equal to 0, so your interval should exclude that.
Yeah, exactly.
So the leftover.
Okay. So what essentially he means is that at least from here, when I have x is equal to 0 and y is equal to 1, what I do know is that whatever thing I draw, it should never be like this. Because if it is like, so it means I know how to draw that rectangle. My rectangle should never contain this point. So that way I know the limit of my b, that it cannot include this one. So let's say if I have a point here and I draw this, what I do know is that my rectangle can never be this. So it does tell us about the dimensionality of the box, that it can never include that. But in principle, we draw a small box around it so that we know that we are talking about the vicinity. It shouldn't be far away from the point. So this much about the existence and uniqueness. And finally, I want to tell you about the slope fields, and I hope I have time. Yeah, I have time. Initially, I wanted to tell you about the dynamical systems also, but this is something that what we are going to discuss has implications in that direction, but I'm not going to. Yeah, you please ask.
Sir, if we have like two unique solutions, तो उसके लिए हमें जो conditions, boundary conditions वो separately calculate करनी पड़ेंगी.
मेरी तो बात ये है कि this is initial value problem. This is not a boundary condition. This whole problem deals with the initial value problem and what kind of initial value would be admissible. We have just seen that we can have a unique solution, infinitely many solutions, no solution. So it means whatever boundary I'm going to choose in the vicinity of my point, the function ought to be well behaved, it should be continuous, and the derivative ought to be continuous. Otherwise, if the function is well behaved, it's continuous, existence of the solution is guaranteed, and if the derivative with respect to y is also continuous, the uniqueness is also guaranteed. But it does not tell us anything about those points where the function is not well behaved, like y is equal to 0, this goes to infinity. So the function is still well behaved because there is nothing wrong with this function. This function was under root y plus 1. It is continuous for all values. Right? But for the derivative, it blows up at y is equal to 0. So all I know is that for this particular point it is okay, but what happens over there where it blows up, this theorem does not tell us anything. So you need to go further, you need to make more investigations which are beyond the scope of these particular lectures, right?
Sir?
और boundary value, initial value को आप confuse ना करें. अभी हम कब बात करेंगे. I don't want to talk about it right now because once we come to the second order, because first order is 1 point. When you talk about a second order differential equation, you talk about 2 points, and 2 points are the minimum that you need to define a boundary. So a first order differential equation cannot talk of a boundary value problem. You need to have a second order differential equation to talk of a boundary value problem.
Sir, अगर हमारे पास like y की negative values होंगी तो उसके लिए भी ये
Yeah, so negative doesn't matter. It shouldn't blow up. It should be well defined. Negative does not mean it is not well defined.
अच्छा वो complex भी हो.
Complex की तो बात है, real values हैं ये.
सर तो complex आ जाएगा ना.
Yeah, so y less than 0 पे, of course. So yeah, so what she is saying is that if you have y here and this y becomes less than 0, then of course this also becomes complex valued.
Even for function
So over here we are not concerning ourselves with the complex values. We want to be in the real domain. So Picard-Lindelof theorem also says that whatever you choose ought to be real positive. Okay? I'm sure that it must have been extended to the complex value problems also.
It will simply change the
But of course I'm
trajectory.
not aware of it. I'm ignorant of it. So if you teach me about that, I'll be very happy.
No, I don't know about it.
But I'm sure they must have been
I'm
extended.
sure there is some.
Yeah, that is my educated guess that they must have been extended. But it's a very good question. Yeah,
जी,
must have been extended to the complex.
बिल्कुल.
The thing that I'm going to discuss now is very interesting in the sense that can we, looking at a differential equation, well, of course it has to be not a very difficult equation, but can we qualitatively say that this is how the solution looks like without actually knowing any method to solve the differential equation. So that is the question we pose ourselves, and then we try and see whether we can answer that or not. So how many of you are familiar with the concept of a slope field, by the way? So first of all, for this kind of a thing, we ought to have this equation. So my right hand side should not contain anything which involves x, the independent variable. This kind of a differential equation is called an autonomous differential equation. And in this particular case, because it is an ODE, this is an autonomous ODE. Here the thing becomes easy, and I'm going to tell you why. So let's say I have dy by dx is equal to y. So if you want to write this thing in terms of in words, so how will you explain it? What does this equation tell you?
It means the field is interacting with itself.
नीचे आए ज़मीन पर आए. There is something simpler than that. That the slope of the function is equal to the function. Right? ये जो आप लोगों के है ना वो field is anyway. So there is a concept of a slope field. ठीक है? I'll tell you what that is, and then we will try and do something about it. So if y is equal to 1, then dy by dt is
1 according to
1 according to this equation. Okay, आपने 1 को भी differentiate करना, don't do that. So it means this is the, let's say this is the slope, and the slope remains the same because it depends only on y. So over the entire x, the slope does not change, and that is the reason of the success of this qualitative analysis. Otherwise, I won't be successful. Well, I will be successful, but then I have to do other things. But at the moment, I just want to tell you, this is something that you can do with an autonomous differential equation, and the basic thing is that over the entire x, the slope doesn't change because it depends only on the independent dependent variable. Okay, now dy by dt is 2. What happens? You will have slightly more, slope will be bigger, so you can just do this. Not this much, but this much. And similarly, you will have slightly more here. If I just make it like never perpendicular, but bigger, 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 bigger. Similarly, over here, -1, slope will be negative. And for this, slightly this. This is a slope field. So now if you want to, let's say, join something, and so you will have to, let's say I want to see how it goes from here to there. So if the points are properly drawn, let's say it is like this. Because at 0 they will come to 0, right? So, and then I can draw something like this, and I can draw something like that, and I can draw something like this, and I can draw something like that, and draw something like that. So now, without solving the differential equation, I have qualitatively told you the solution. So once you solve this differential equation, you will see that the solution would look like this. But here, by using the autonomous differential equation and the idea of slope field, you have qualitatively explained how the solution would look like, even if you do not know how there's any method to solve the differential equation. Okay, questions? Please ask.
So is this related to slope field okay to a scalar field? Scalar is slope field?
The slope है यार, it's just the slope, the tangent that you are so familiar with. It's the same idea. Slope, tangent. You are just drawing the tangents, right?
तो इसमें autonomous ODE की definition क्या है? मतलब exception क्या होगी? क्या बनाएंगे इसको?
सिर्फ यही बता रहे हैं कि जब when it does not involve x, so when I'm going in x, the slope stays constant, and that is it. That is the reason that you just drew one slope, and over the entire minus infinity to infinity, you just drew those lines because you knew that the slope is not changing with x. Had it been changing with x, then it will be a problem. So if, let's say, you encounter this kind of a thing that I talked about, then of course you can do something, but then you have to fix something. So let's say x is equal to 1, 2, 3. So again you can, so it will be shifted, but yeah, you can talk about it. But you can't, but at every point, what you will see is that at every x it will be changing. Okay? So that is why it's a big problem. Yeah.
सर इसका asymptote बनेगा? Asymptote.
Asymptote क्यों बनेगा?
इसका बनेगा क्योंकि like gradient increase होता रह रहा है ना?
तो increase हो रहा है मतलब ये तो आपके पास equation जो है इसका asymptote तो उस चीज का बनता है जहाँ पे कोई चीज blow up कर रही हो. This is well defined over the entire range.
So लेकिन अगर जैसे y as it approaches infinity gradient भी infinite होना शुरू हो जाएगा.
Okay, so yeah. So I can say y is equal to e raised to power x. So when x goes to infinity, this will be infinity. लेकिन उसको आप ये नहीं कह सकते कि वो ये जो चीज है ये infinity को ही जा रहा है. लेकिन यहाँ पे कोई चीज blow up नहीं कर रही, कोई asymptote नहीं बन रहा. This is steadily increasing till infinity. There is no idea of an asymptote. Asymptote का मतलब है you are approaching a point and you are encountering singularity. For that, you ought to have something in the denominator. Numerator में there is no concept of a singularity. यानी वैसे तो आप हर जगह पे ये कह सकते हैं कि y dash is equal to y, जिस तरह भी आपने कहा y goes to infinity. But that is not the point. It means it is growing indefinitely. It is not encountering any singularity. Singularity is associated with the denominator and with a zero appearing over there, which blows the whole thing up. Okay? So I stop here. Maybe I just need to talk about the phase diagram and attractors and repellers and the stability maybe tomorrow, not tomorrow, on Saturday for 10 minutes, and then we will go on and talk about the differential equations in all their glory. This is technical stuff. This is hard stuff. The first lecture ought to be discussing these final points, and then we can talk about the rest later. Questions, please ask. We have a lot of time. 11:30 you will begin, right?
Yes.
So we have got half an hour to discuss anything that you want to discuss, and I have the answer to. Thank you for putting up with me. No.